All right, today we're going to talk about binomial radical expressions. And we're going to talk about adding and subtracting them in particular, okay? So basically what we're saying is we're going to talk about combining like terms because that's what we're doing when we're adding, okay? So there's a couple different rules we need to go by when adding and subtracting radical expressions. Excuse me. The first one is the radicand, which is right here. The radicand needs to be the same, okay? So in this case, square root of 2 plus 3 square root of 2, the radicands are the same, so that's 4 square root of 2. The other thing is the indices, the index, right there, also needs to be the same. So in other words, we can't say square root of 2 plus cube root of 2. That is not going to work because they're not like terms. We also can't say the fourth root of 5 plus the fourth root of 10. That's also not going to work. Okay. Now let's look at some examples. In this case, the radicands are the same, the indices are the same, so all we have to look at is the coefficients. 3 subtract 2 is 1, okay? So we would just write that as 1 square root of 5x, or simply square root of 5x, okay? Example B here, the bases are the same, so we can't do anything with that. That is what it is. We cannot combine anymore. And we look at C here, the indices. Here we have cube root, here we have fifth root, so we can't do anything with that. So we leave that the way it is. All right, now let's look at something else. We also want to make sure that we have simplified the radicals, because when we simplify them, sometimes we come up with radicands that are the same. So let's look at an example here. Square root of 12, we can simplify that to 2 square root of 3. Okay? And square root of 75 can simplify to 5 square root of 3, and then square root of 3 is okay. Now look what happened. We went from 3 completely different radicands, but then once we simplified, we have 3 identical radicands. Indices are the same, so therefore we can combine them. 2 plus 5 is 7, minus 1 is 6. So the answer is 6 times the square root of 3. Okay? Now if we look at this one here, see if I can raise this. Maybe you can see it a little bit better. All right, so let's take this one on. So we have cube root of 250 plus cube root of 54 minus cube root of 16. The indices are all the same, but the radicands are different. So we need to see if we can simplify those. Can we? Yes. Square root of 250, if you can't do it off the top of your head, we can break that down to 2 times 125, and this becomes what? 5 times what? 25. This becomes 5 times 5. So we're looking at cube roots, so we need triples. So that gives us 5 times the cube root of 2, because it's left. Okay? Now, 54, okay, we're looking at cube roots. 54 breaks down to 2 times 27, 3 times 9, and 3 times 3. All right? So now we've got 1, 2, 3. Okay? So that comes out. And then we've got cube root of 2, because it's left over. Okay? And then the cube root of 16, Again, if we use the factor tree, 2 times 8, 2 times, 4, 2 times 2. So we have 1, 2, 3. So that is 2 times the cube root of 2. Now, look what we have. We have 3 radicals in which the index are the same and the radicands are the same. So 5 plus 3 is 8, minus 2 is 6, times the cube root of 2 would be your answer there. All right? I'm hoping you can see this. If not, we'll just get through it as best we can. Okay, now we're going to look at multiplying binomial radical expressions. Don't let this scare you, okay? We have 2 binomials that we're multiplying together. We have 1 term, 2 terms, 1 term, 2 terms. So those are binomials. We're just going to add them. We're going to use double distribution, which you know is FOIL, okay? So 4 times 5 is 20. 4 times 4 square root of 2 is 16 times the square root of 2. Here we have 2 times 5 is 10 times the square root of 2. And then finally, the last term, we have 8 times the square root of 4. Now I know what you're saying. 4 is a perfect square. We'll get to that. Okay, so let's combine. We're going to go one step at a time here. So 20 plus, we can combine these because the radicands and the indices are the same. So 16 plus 10 is 26. Square root of 2 plus, well, this becomes 8 times 2, right? So that becomes 16. So now we've got 20 plus 16, which is 36, plus, right here, 26 square root of 2. And that then would be your final answer. Okay? Let's do another example. Let's move on. Okay, now, we've already talked about conjugates, okay? We know, for example, that the conjugate of square root of 3 is negative square root of 3. We know that the conjugate of 5 plus square root of 2 is 5 minus square root of 2, okay? These are conjugates. These are called complex conjugates because they're dealing with complex numbers, okay? So our rule we had about multiplying conjugates still applies here, okay? If we have 2x plus 3 times 2x minus 3, what I told you is just square the first term, 4x squared, and always subtract the square of the last term, okay? So if you were to FOIL these, this is what you'll get because the middle falls out. Okay, and that's the characteristic of conjugates, which is really kind of sweet. Okay, so let's practice on this one here. So we square the first term, 25, always minus. Square the last term, that is square root of 49, which is 7. Okay? So 25 subtract 7 is 18. And that is the answer to this multiplied by this. So the radicals drop out. Okay, now we're going to rationalize the denominator. And this can be a little tricky sometimes just because of the algebra. So if you remember, the complex conjugate of root 5 minus root 2 is root 5 plus root 2. So that goes here. And like I've told you before, the only way we can do this is because this right here is equal to 1. All we're doing is multiplying that expression times 1. We're merely changing the appearance to make it easier to calculate. Okay? So now we just multiply here. So we get 3 square root of 10. Now we multiply here. Plus 3 square root of 4. And I'll come back and clean that up. Okay? Now we're multiplying conjugates. So right here, square root of 5 squared is 5. Square root of 2 squared is 2. All right? So now we come over here. We have 3 square root of 10 plus square root of 4 is 2 times 3 is 6 over 3. All right? But now we're not finished. We need to look and see always if we can simplify. Just like we wouldn't leave 10 fourths as an answer, we would simplify that to 5 halves. We have to do the same thing here with this complex fraction. So we need to look at the coefficients only. 3, 6, 3. Is anything common to those 3 coefficients? Yes, 3. So we divide everything by 3. So we get square root of 10 plus 2 over 1. So that is our answer. Okay? Now, remember, rationalizing the denominator means that we are eliminating the radical from the denominator. So if you still end up with a radical in the denominator, you've done something wrong somewhere. Okay? Because that defeats the whole purpose of rationalizing in the first place. All right, let's do one more example here. I think is all we have time for. Okay? So we're going to multiply here by square root of 3 plus square root of 5. Okay, multiply across. We get 2 square root of 21. Here we get 2 square root of 35. Okay, over square of the first term, 3, square of the next term, 5. Okay, I can see this one's going to cause some issues because of the negative. Okay, so if we simplify, okay, so now we look at our coefficients again. Let's look at our coefficients here. Okay, so we can divide out a 2. So if we do that, we get square root of 21 minus square root of 35, okay? And we have a negative here. And I want to look at this real quick because I think we have time. If we separate this out, 2 square root of 21 over negative 2 plus 2 square root of 35 over negative 2. Well, look what happens. Those cancel and we get negative square root of 21. These cancel and we get negative square root of 35. And that maybe helps explain why that's that way. Okay? So, you know what it means when the last slide's blank? We're done. I hope this helps.